turn him back over to being the presenter, but Tobias Harrison-Noonan is the Director of Business Development at Instrumental. And he's partnered with leadership and contract manufacturers, hardware providers, and industrial software companies to develop Instrumental's continuous improvement and failure analysis software tools across a variety of industries and use cases. Tobias spent 6 years at Apple leading product design engineering teams focused on sensor and touch design across a wide range of Apple Watch and iPhone programs. He managed teams of engineers focused on owning failure analysis, root cause identification, and Instrumental's vision of self-correcting manufacturing processes. Tobias holds an MS in Mechanical Engineering from the University of California in Berkeley, which is, I believe, near where he's going to be presenting from, which is in San Jose. And with that, Tobias, welcome, and teach us something about artificial intelligence and root cause and eliminate design defects, et cetera, et cetera.
Tobias, are you able to make your full screen?
Yes, I can. Let's see here.
One other side note, all attendees at the very top and the middle of the screen, you can change what you're viewing. Just click on the view everyone and adjust it to what you want to see. And to that, Tobias, you're on.
Excellent. Well, thank you, Peter, for that wonderful intro, and Mike, and to the SMTA for hosting me here. Excited to share a little bit about Instrumental, our technology, and some real world use cases. Peter already gave you a pretty comprehensive background on myself. I'd actually love to hear in the chat from all of you guys. I saw some people from Canada, from Mexico. Always like to hear if you could just introduce yourselves. I think chat should be in the top right, where you're calling in from. And I always like to hear, what is the first hardware product that you ever worked on? First product in any capacity. Just post it in the chat. I'd like to see how people got started. So again, my background is mechanical engineering. Did product design at Apple for a number of years, as Peter mentioned. And what that means is I spent a lot of time in factories, debugging issues, doing design, failure analysis all around the world. So I've experienced a lot of these inefficiencies firsthand over those number of years. And now I'm leading some technical and some business development teams here at Instrumental. And what we're going to cover today, excited to share. First, we're going to talk about some of the challenges that we're seeing in the industry. And then we're going to talk about the technologies that are able to overcome some of these challenges. And then we're actually going to go through some real world use cases where Instrumental's AI was applied to some of these challenges. So let's dive in. And as Mike mentioned, post questions in the chat throughout. We want to hear your feedback, and then at appropriate times we'll have a few stopping points where we can address some of those, but we definitely want to hear your feedback. All right, so let's dive into it. I'm getting a little bit of feedback from somewhere. Can we just double check that everyone's muted? I think we're good there. So why is it so hard to manufacture products? Why isn't this getting easier over time? A lot of people think that this should be getting easier, when in fact hitting these production KPIs is actually getting more difficult. And there's a few reasons why this is happening. Number one, products are getting more complex. We're putting more and more technology, more stuff into similar or sometimes even smaller form factors. Schedules are always a factor. Tight schedules, we need to ship stuff faster, need to ship stuff on time. And the third and potentially the largest pressure is the global health situation, travel restrictions. What we were just talking about with Peter and Mike, having to run remote builds, supply chains getting disrupted. All of these are adding extreme pressure to our production. And it's causing a lot of strain on our teams that are still trying to hit this same level of quality. So what are we doing about it? Well, a lot of people turn to their team. How can I leverage my team to overcome these obstacles? And we surveyed operations and engineering leaders from 100 different organizations within the industry, and the number one thing that was slowing them down, that was stopping them from resolving these supply chain issues and driving those KPIs, was team bandwidth. So across the board, the team is the number one gating item. A lot of these teams are overworked technical staff. We're trying to squeeze more out of existing teams. They're being stretched to collaborate, with their counterparts across the country, maybe across the globe. All of this collaboration takes a lot of bandwidth, but the core issue still comes down to the team is the most important factor and the gating item. So what are teams spending their time on? Where is this time being spent? Again, from these same 100 organizations, we collected data, and shockingly, only 23% of their time is spent on what we would describe as core engineering work, the design and innovation. Only 23%. And all of the rest of the time is spent on these other tasks like collecting data, parsing data, communicating status updates. All of these tasks that should be able to be either accelerated or automated by some type of tool. And the reality is we've set up these extremely brittle supply chains. We've tuned it to be just right, just in time sort of supply chain. And the disruptions that have come recently with the travel restrictions and the chip shortages, they have pushed a lot of these supply chains to the breaking point. And we're starting to see the impacts on teams getting overworked, schedules getting pushed out, quality taking a hit. All of these are not things that we want to see. So what are teams doing to actually address this issue? What kind of tools can they use to address this huge inefficiency here? Let me see, I lost my clicker. There we go. Well, the reality is a lot of these tools that are being used are extremely old and outdated. We're talking about manual data analysis tools like Excel, logging data, parsing data, looking for correlations, human inspection. Very few organizations are actually utilizing more advanced build analytics tools or BI or even AI is only down at about 11%. And it's these outdated tools that are causing these inefficiencies. They're holding the teams back because they're eating up such a significant portion of our engineering team's time. And the organizations that are proactively adopting these technologies, we'll talk about some use cases with instrumental organizations like L3 Harris, Honeywell. These organizations are getting these outsized competitive gains because they're able to automate a lot of this data analysis, data parsing, and then their engineers can actually spend more time doing actual engineering. So I'd love to hear from the audience here. From your experience, have you tried what types of data analysis, thinking about hardware production, what type of data analysis, build tools have you used to try to make your data analysis more efficient? Have you guys had any success with any of these tools, or maybe unsuccessful implementations? Go ahead and just post it in the chat. I always like to see what types of tools teams are trying out.
So we have gotten some feedback in the chat. We've got David Burris from the Czech Republic. We've got Guado Borg. If I butcher these names, I apologize. Borges from Boss, Germany. Mutaz Bora from P-Semi in San Diego. So we've got quite a crowd from around the world here.
All right, excellent. Welcome. I see he's designing PCBs for large systems at IBM. It's a great start. It's exciting. All right, keep the chats coming. Again, want to hear about systems that you've used for data management of your production. All right. So what we are hearing from the large players in the industry that we're working with, they know that their production data, their product data is valuable. They have these huge amounts of data, but they feel that they're not getting the full value out of their data. They have this huge data store. This is test data, functional data that sits around in the factory. And the key to driving the metrics that they care about, this is the production yield, reducing rework and scrap, improving the overall quality and reducing returns. How they get there is by actually leveraging this huge amount of data that they already have. So how do we do that? This is where a manufacturing optimization platform comes into play. So that's what Instrumental is, a manufacturing optimization platform. And what we're seeing with the big players is the data is locked in these silos. So this could be at the final assembly site. We've got functional tests, we've got measurements, and then distributed throughout the supply chain as well. We might have upstream suppliers with similar test data. And all this data is typically just stored locally in the factory, and not that much is done with it. You get a pass-fail results, but then there's not additional post-processing done. So there's all this valuable data sitting around, and that is where we start. It's just the start. And from there, so what Instrumental does is it aggregates all of this data across your supply chain. We aggregate it into what we call a digital thread. So this is in our cloud database. So it's remotely accessible. Everything is serialized, so everything is traceable, and everything is secure because it's in a managed cloud. And we don't stop there. Now you have the test data, and the special sauce of Instrumental is we enrich it with high resolution images at these key stages of assembly. So this could be during final assembly, adding key checkpoints in. We also add in sub-assembly imaging, component imaging upstream. And so what this creates is you now have a complete historical record, a complete digital thread of every single unit that you've built that's centralized in a cloud database. And then the possibilities are just limitless once you have all this data in one spot. And we integrate with existing test systems. We do have some existing camera stations that we can provide as well. We can get into that later. So once you have all this data, that's where the AI comes into play. And the AI on a daily basis starts automatically crunching through these terabytes of data so that you don't have to. Again, coming back to engineers' time being spent parsing through data, that's not an efficient use of engineering time. Yet, unfortunately, that is the largest chunk of where engineers are spending their time. So we have AI that's going to look through all this data for you. It will automatically highlight new issues. And this is what I'll get into a little bit later on about the secret sauce of our AI. Is it requires very little training. It's completely unsupervised. It's going to start finding things for you. And once it does find an issue, you can actually trace it back because you have this complete digital thread. You can pinpoint it to earlier on where the issue actually originated. And then you can actually fix the issue at the source instead of just screening it out later on. And we also have AI that will actually suggest root causes and correlations. So it's going to look at your test data, and we've got some examples of this later on. It'll look at your functional test data, and it will suggest a correlation between that test data and what is going on in the image during the assembly process. So extremely powerful correlations, as well as all this remotely accessible data is what accelerates the failure analysis that these engineering teams are doing, especially remotely. I'll pause here and check in with the audience. Any questions so far on this concept of a manufacturing optimization platform that we presented here, aggregating data, enriching it with these high resolution images? Feel free to post them in the chat.
We don't have anything posted in chat yet, but I want to remind folks that if you have any questions as we're going, you can put them into the chat and we're happy to address them.
Thank you, Mike. More questions the merrier. So post them in, and we will either address them live or save them for the end. All right, let's talk about what we do with that data. So a lot of traditional technologies are very focused on the in-factory experience. Over here at the operator side, there'll be a pass-fail result that's given live, and then that's it. The data doesn't go anywhere. You get your pass-fail results, and that's the end of the data. And what Instrumental's platform is extremely unique in is getting all of this data, getting it in front of the right people, all in real time. And so what that means is, because all of this data is centralized, we're able to create dashboards for executive teams to monitor their programs and do high-level risk assessments. The mechanical engineering product design teams are using the same database to do their remote failure analysis, to investigate issues. The quality teams are looking at top issue Paretos. They're prioritizing which issues to tackle on a daily basis. And with the same system, it ties in, and you're still able to do that standard pass-fail judgment on all of your known issues. So having it all centralized really amplifies the power of all this data. All right, let's talk a little bit about what's special about this AI. How does it actually work? AI, it's a buzzword. People throw around AI all the time. I'd love to hear again from anyone in the audience. Have you attempted to implement any type of AI solution? Have you tried some image-based AI machine learning? Have you tried AI on your test data? Because it's a very broad category, and a lot of people have mixed experiences with trying to implement AI. So ours is very purpose-built for manufacturing. As I mentioned before, on the images, so what our AI does is it's called unsupervised learning. So it's not like a traditional AI model where you have to actually teach it what to look for. Instrumental's AI, it actually, you just put in the images and it learns what is normal. And then after just 30 units, it will start highlighting anything abnormal. So instead of you training the AI, it's actually the AI automatically highlighting things to you. So it's this very low lift, unsupervised AI. And it's also great at difficult to define defect types. So think about a blob of glue. It's amorphous. It's difficult to define with standard machine vision algorithms. Glues, anything, wiring, connectors, anything that's difficult to put concrete parameters around is a great application for this type of AI.
Tobias, what information do you use to establish your 30 known products? Is it 30 good known products, and use a variety of different information to identify what is a known good quality product, and then you start looking for mishaps or misalignments or other types of data that indicate that there's a quality issue?
Yeah, that's a great question. It would be great to show in the product as well. I can show you a little quick preview. We take 30 units. They don't have to be good units. Why don't I just show you over here quick? You take 30 units and it will automatically identify. Let me hop into here. So let's say you put in 30 units of your device. It's going to automatically suggest potential issues that are popping up. So you can see here, this is with no training. It says here, this looks like something abnormal. This looks like a missing screw. It doesn't, I haven't told it what to look for yet. And then you go in and you confirm which one of the issues are true defects. So I might confirm this as a true issue, and then I give it a little bit of feedback that this is the failing threshold, and then I could save that test. So you just start putting in images, and then it's an interactive process from there where you log in and you just do a couple clicks to confirm some of the defects.
I'd like to elaborate on my question. So you used a screw as an example. If that screw had a torque value and it was being put in with a system that tracks data on torque values, can you incorporate that data?
Yeah, that's a great question. So yes, we take in, if you look at the types of data we take in, this is the digital thread that I was referring to. We have images from an upstream, this looks like an enclosure supplier. Our final assembly line, we have about 4 or 5 images. And then we also have test data, which is where you could take in torque values for specific screws, other machine parameters, any type of data that is valuable to your product, you can put into this system, and then you can start getting more out of that data.
Okay, we have a question coming from the audience. I'm going to read it, and hopefully I read it correctly. How are you managing TBs of data in the cloud for speed and access for queries? Can imagine slow response times.
Yeah, it's a good question. Looks like from Michael here on the amounts, the terabytes of data that are coming from the factory into the cloud. There's a couple components, Michael. We do have an edge computing device. So most of it happens in the cloud. If we're looking at the retroactive AI parsing through, looking for defects, that happens in the cloud. and then you log in and you can access that in real time. The live detection in the factory that requires the 5-second response time, that is actually processed on a local computer there on the edge. So that gets rid of the need to send stuff to the cloud, process, and send back down to the edge. So there's never any delay from the internet connection there.
So I guess the
Let me
question
know, Michael.
is, how quick do you catch a defect?
So if it is set up live on the line, it will give you feedback within 5 seconds. So you get that live on the line, immediate feedback, and then there's additional processing in the cloud that's looking for even more potential defects types. So it's a multi-part system about catching known issues live on the line, as well as parsing through on a daily basis to look for new issues as well.
Thank you.
Good questions though. Keep the questions coming. We can hop back and go through other parts in the application as well if that's useful. The correlations, Mike, kind of to what you were asking on the screw torque and the image of the missing screw. I can show you as well. The AI can actually find correlations between those parametric values. So if it's screw torque or if it's your antenna test, typically it's a very manual process to go plot out that data, look for correlations. It could take weeks to find a root cause, where with instrumental, the AI will actually look for correlations between those test values and the images. And so it's going to suggest potential root causes for you. So it's cutting out a huge portion of that manual engineering time. All right, we've got some use cases to walk through here to give you a little more concrete idea. But again, questions, keep them coming in the chat box. The types of use cases. So Instrumental works with a pretty wide variety of customers, from the high volumes like the Boses, the Motorola's of the world, to lower volume, high criticality, Honeywell, L3. Really, it's anyone where quality is paramount, where quality is something that they will invest in and it's important to their brand. So this is a great use case here with Lenovo. Again, leading electronics brand, mobile phones as well. We had a pretty comprehensive deployment. We were collecting images. You can see down on the bottom of some of these complex PCB assemblies at, I believe it was 12 different points throughout their supply chain. They implemented us during ramp and production, throughout mass production. And one of the largest issues that they had was at the end of their line, they had a fallout, which was then extremely expensive to rework. So they had a bunch of devices that were failing, and then it was very pricey to go back and rework because they caught it so late in the assembly process. So with Instrumental, because they added in these checkpoints throughout the assembly process, they were able to catch the defects earlier on and actually rework them right at the spot. So they actually had two benefits here. The rework became much cheaper. It actually resulted in what turned out to be $1 per unit savings, which added up over millions of devices was massive savings for them. And also just reducing the total amount of rework, because they were actually able to catch it right at the spot of failure, then they could actually drive for a process improvement. Let's see. Oh, I see a question from Fabian. How do you control external factors such as vibrations, lighting, part markings in order to get accurate data values? Good question, good question. So I'm assuming you're referring to the images that we're collecting for our system. There are two different ways that we get images into our system. One is from existing equipment on your line. This could be other cameras that you have, AOI. We can integrate with those and ingest those images into our application so that you have all your data in one spot. So if that's the case, we'll work with the customer, we'll work with Lenovo to make sure that their images are meeting our standards. If the customer does not have images already on their line, they don't have cameras, we can actually provide, we have a little drop-in hardware camera station that's optimized to take these high resolution, consistent photos. So we actually have a team that will help design, if you're asking about the placement, we have a team that helps to design fixtures and helps to design the lighting to keep it extremely consistent from device to device. You had a question about variable part markings. So the AI will pick up some variations that you probably don't care about. For example, here it looks like it's picking up maybe the serial barcode is moving around a little bit and it has some black dots. So the AI does pick up a lot of different things, and that's the power, is it picks it all up automatically, and then it gives the user the power to review those, and with just a few clicks, then you confirm which ones are true defects, and then you set up a test. Or for the variable part markings, maybe you say something's not interesting, and then it tells the AI to ignore that. Good question, though. All right, a few more use cases here. So a few more details on the Lenovo one. They were actually in a hurry to accelerate through their ramp in production, and instrumental system designed to be set up as soon as possible. As I mentioned, it just takes 30 units to get started. We actually deployed in just 4 days on their production line, started collecting images and talking about discovering new issues, the unsupervised learning that I mentioned. We were able to discover 130 new defects types that they did not previously know about. So this was huge for them, because then they're able to proactively go tackle those issues.
Could you give an example of some of those issues? Was it, tombstoning? Was it misalignment? I mean, what 130? That's a lot of new defects. So, can you elaborate on a couple of them?
Yeah, definitely. The top ones, I believe, from Lenovo, they had some glue, some conformal coating that was protecting some key components on their circuit boards, and that coating was in a lot of different places. So discovering defective coatings, they had spring pins. You can almost see them here, spring pins that were grounding from the circuit boards. These are grounding for antenna performance, grounding to the housing. They had missing screws, is a very common one that they had, damaged connectors. It's all sorts of assembly level defects, less focused on, I would say, the traditional SMT level, like component level. So if you're looking at like a PCB like this, we can catch some standard things like component damage. You can see a little corrosion here and there. But really, it's the defects that they didn't already know about. Those are the ones that come to bite you later on. And those are the ones that our system is able to call out for you so that you can tackle that new issue in one day instead of waiting a couple weeks. So again, this isn't the Lenovo, but similar types of defect. This is glue overflow on a connector. This was corrosion on some components. Here's a damaged board-to-board connector, unsnapped connectors. This one's really tricky because this won't fail a functional test. This will actually pass, and this would probably fail in the field. So huge variety of different defect types.
Good examples, and we now have 3 people asking additional questions. Can you see them on your chat log, or do you want me to read them to you?
No, I can see them here. So we've got a couple good ones. There's a 5-second defect realization time on the line. Is there a real-time feedback loop with suggested solutions to create a real-time fix? That's an interesting question, a suggested feedback loop. So the real-time component, once I confirm an issue, let's say I confirm, yes, this is a glue issue, then in the factory, there's a little red light, green light next to the camera station. It'll give you live feedback. It will tell you that it will highlight this region here. It'll say this region has failed for this test. So it'll tell you exactly what's going wrong. And typically that is how they drive a process improvement. Because if the operator is right here and then it goes to the test and it says, oh, you have a bent pin, or you have a missing screw, then normally the line leader uses that to directly feedback to the operator if it was truly induced right there on the line. If it's a more complex failure mode that was maybe induced upstream, then you need to jump into this web application and do some additional investigation.
So the time frame to implement a fix is going to be based upon what the problem is and where and how to fix it. So in some cases, it can be instantaneous. It sounds like you can actually stop a line from spitting out a lot of bad parts. And depending on where the defect is coming from, it might be a screen printer, it could be a pick and place, it could be a number of things. So whatever it is, you fix it immediately if you can. It might be something that might take a little bit longer to fix the fix or implement it.
Exactly. It's the key value is starting, like, knowing about that defect as soon as possible. Maybe you fix it in 2 minutes because they can fix it right there on the line. Maybe it takes 2 hours, but somebody logs in online. But either way, without a system like this that's proactively finding things, it can take, in my experience, an issue like this, a little glue overflow. If you don't see that, you're probably going to find that 2 weeks later in a reliability test when corrosion comes up on your failed unit. So knowing about it sooner is always better.
So essentially, the real time is there. It's going to pick something up instantaneously and let somebody know, right? I mean, he's saying 5 seconds. I would imagine, depending on the line and how it's constructed, it is absolutely feasible to consider that you can catch defects within seconds.
Yes, yeah. So we do have that the real-time feedback to fail the unit. Then what is the fix is a different question.
Okay.
But
Michael, if that doesn't answer your question, please chime in further and we'll address that further. The next question is, how quickly, i.e., number of false calls, will the AI stop highlighting anomalies which the operator classifies as passes?
Ooh, good question. This is from Zoltan. I always love to hear examples too. So Zoltan, if you have a specific use case for the type of defect, it's always interesting to hear what types people are struggling with in terms of false calls and passing units. So stop highlighting what you've already classified as pass. So what you can do, if you need to adjust the threshold live again, so you can adjust your AI tests remotely. So let's say my factory is, over in Pennsylvania or in a different state, but my quality engineers are working from home because that's how we're all doing these days. You can log in to manage your tests in the app, and then you can give feedback. If you actually thought this unit should have been passing, you can just adjust it here. And then when you update the model, then you just hit like update the AI model here. And then it'll be about 2 to 3 minutes before it processes that and then updates the model in the factory. So it's actually really fast. It's a much more agile system than traditional machine vision. You probably send someone into the factory and start retuning the machine, but someone's got to physically be there. So here you can do it remotely in just a few minutes. Let me know if that doesn't answer your question. Yeah, in the matter of minutes, it can be updated.
And so a supervisor can easily override an operator. So if there are false calls, we could adjust that pretty much on the fly. Somebody can be remote. A supervisor can be remote. They see that the operator's, pushing the wrong button, or they don't agree with what the operator's doing, and they can adjust it instantaneously.
Yep, exactly. And you can, again, the advantage of having it centralized here is that supervisor can actually see what's going on in real time. They could see units coming in from, a minute ago and see how it's performing without having to sit there on the line. So they could send it to, their quality engineering colleague as well, send them over the link, and they could kind of collaborate back and forth on how are these tests performing? Do we need to tune this one? Are we getting too many false calls?
Okay.
We got a few more good ones here. Yep. Let's see. Can the system recognize a similar type of defect on different products? From David. Guessing you're looking like, can we look at solder bridging between different products? The short answer is we will need to retrain on the new product. So we're not actually taking learnings from board 1 and applying it to board 2. But because the number of example images is so low, typically it only takes 1 day to set up new products. So technically it's not transferring the AI from one product to another, but it's easy enough to set up. We've got customers running 10, 15 different products through their assembly lines, and the AI is learning on each one of those products.
So the short answer is yeah, the system can recognize similar type of defects based upon what it learned on another product.
It doesn't technically take the learnings from one product to the other. So it does start fresh on the new product.
Okay.
Yeah, it does start fresh, but because the setup process is so simple, again, you just run 30 units through and then log in here. It's easy enough that our customers have set up, over a dozen products within the same line.
Okay.
Yep. A few more here. I do have some other exciting use cases too, but these are some good questions. Software capable of using data and images from 5DX or similar soldering to inspection. I believe the 5DX system is taking X-rays. I think I've seen X-rays at a slight angle on like BGAs. Fazari, if you can confirm that that's what you're looking for, then the answer is yes. We can take in, we actually have a pretty cool, I could show you here. if anyone's interested. We've taken in X-rays as well. So we can take in X-rays of complete systems, X-rays of PCBs. It all comes into the same database. You can run the same AI on the X-rays. It'll find new issues for you. And again, it'll be accessible for you to do any remote failure analysis in our system. So yes, absolutely, more data, any data that is valuable to you, we can, image data, parametric data, we can implement into our platform.
Great, thank you, Tobias.
All right. Was it X-rays that you were referring to?
Yeah, just an X-ray based technique to identify that type of stuff.
Yeah. I can show you quickly here. Let me pull up the X-ray just to give you one quick example, and then we can hop back. So here's an example of pulling in X-ray images. This was less focused on soldering defects, but you can see just scrolling through the units here, you can see we're able to pick up, here was like a missing screw that it picked up. There's a lot of interesting things that you can see in X-raying these devices, extra screws, missing screws. And so the same could be applied for the 5DX, solder inspection.
I'm assuming you can take those images from the X-ray and correlate them with other data to get out, what you're, to narrow it down to eliminate false calls and or identify true defects.
Yeah, so that's a great point. You're talking about correlating the X-ray images to other data points?
Yes.
Yep. So we can do that. I'll show you a quick example of that, specific to functional data. Actually, let me pull up a use case here where that was extremely impactful. So this was with a large defense and communications leader. Unfortunately, we can't share the logo here, but I'm sure you guys have heard of them, making a radio product, and they had an issue, a yield issue that had been nagging them for 5 years. They hadn't been able to fully root cause. They were just living with this issue, and it had to do with their audio test, their microphone, and they implemented instrumental. And after only 250 units, we were taking in the audio test data, so all of their microphone test data at the end of the line, and then we had images of their microphone placements, and we could also see cavity numbers in some of their molds. And so combining those images with the test data, they were actually able to test and evaluate dozens of different hypotheses on what could be causing these microphone failures. And in just a couple hours, they were able to fully resolve. They were able to identify the hypotheses, eliminate a whole bunch of ones that weren't correct, and then work towards root causing this issue that had been bugging them for the longest time. And so this is, Mike, to your point on the power of having the test data and the images is really more, it amplifies the value putting them together.
So we have 2 more questions in the chat right now.
We do. I do see, let's see, Michael, multiple plants in different locations.
You missed one.
Using this.
There's one right before it from Zoltan.
Oh yes. So Zoltan, this is following up on the retraining. In conclusion, it's a human decision to stop calling out an anomaly, not the AI does it automatically. Correct. So the AI by default is highlighting potential issues for you. So this is the dead simple, zero effort from the user to set up. You just start putting images in, no training required, which is very different from a lot of systems. But then you are correct that if you want it to stop highlighting these new issues, or if you want to kind of tune one of your existing tests because there was a false call, there needs to be some amount of human feedback. So the AI will bring it to your attention and then make it as easy as possible for you to tweak it. But yes, you are correct.
Thank you.
And
one more.
Michael, multiple plants in different locations manufacturing the same product aggregate data together to analyze the product's quality performance. That's actually a great point. Is when you're manufacturing at multiple locations. So a lot of manufacturing orgs might have two different plants that are manufacturing the same product, and it's very difficult to manage all the production and the tests independently with on-prem systems. So Michael, to your question, yes, that is a prime example of why having a centralized database to manage all of your tests, you can apply it to both factories. So you could have, you could be running actually the same tests. You could have images flowing in from two different factory locations, and you could align all of that to, it's actually running the same AI test at both factories. You could look at performance between factories, and it's all rolling up to this one sort of centralized database. So yeah, that's a great use case of how to manage multiple locations at the same time. It ties into, there was another use case, here with an electronics apparel product where they're using instrumental throughout their entire supply chain. So multiple upstream suppliers, as well as at their final assembly and at their returns and refurbishment center. And they actually replaced their existing data management infrastructure. They're using instrumental as their primary test data infrastructure. So they were able to save over $1 million just in their test infrastructure. And then on top of that, getting all the benefits of accelerating the speed of root cause analysis and driving yield improvements. And that applies beyond just final assembly. Getting all of those benefits upstream as well was a huge win for this team. All right, excellent. Well, I think we went through a lot of great examples there. Other questions? Mike, happy to walk through the correlations as well. I showed the use case of the correlation. I could actually show it in the app here if you want to see it live. So one example, if I have test data that, again, typically this test data is just stuck in the factory. So here I have some antenna test data. And you can see I've got some units that are failing for low antenna power. If I click into this is live on the fly. The AI is actually looking for correlations. So I'm going to select just these 8 failing units. And here it's looking through all the images, trying to find out what do these 8 units have in common that could be causing this low Bluetooth power. And sure enough, right at the top, it's suggesting a root cause. It looks like it found some units with a missing metal tab. This is a grounding shield. And if this isn't grounded properly, good chance that that's going to mess with the Bluetooth performance. So just like that, no input required. I can log in and investigate, and it's going to automatically suggest root cause and correlations for me. All right. Well, I think we made it through a good amount of content there. Any other questions? Any other questions from the audience? Would be happy to address them now.
So it looks like there's no more further questions in the chat log, but if anybody else has any other specific questions on how the AI helps identify root cause, we're more than happy to stay on with you. Tobias, was there any other, I know we jumped around a lot, we started answering a lot of questions. Did we miss or mess up your presentation by asking so many questions, or did we hit all the salient points of your presentation?
No, the questions were great. Questions really were very on point. I think we hit everything we need. There's always more use cases to go through, but I think we hit all of the critical points.
All right. Well, with that,
So
I'm going to
we're good to go.
Now pushing 4 o'clock. For those of you that would like to stay on and explore this a little bit further, ask additional questions, we're going to stay here. But that does conclude the primary presentation. We appreciate all of you joining, and again, stay with us if you'd like to stay on.
Absolutely, and along the same line, having future presentations like this and live meetings coming up during the fall. So make sure you go to the smta.org website and go to the Massachusetts or Boston chapter to look up what's coming up next. But please stay if you've got questions. We'd love to entertain any of them that you have. I'm sure Tobias has any answers anyone may have questions for.
We do have another question.
Hi, Tobias. Hi, this is Mike Jansen.
Hi,
I have a question with respect to the X-ray. It sounds like you'd be able to do gross defects with respect to, like you mentioned, screws, maybe misaligned components. How about getting down to like when you have small components and you're looking at like void analysis? Is that anything that it's capable of doing?
Yeah. So good question. The software in our platform is capable of detecting those types of defects. It is all about getting an X-ray with the right resolution to be able to see it. So a general rule of thumb is if you can see the defects in the image or in the X-ray, if you can see it with your eyes, our AI will be able to see it. But again, our AI isn't magic. So if you have a large X-ray and there's only like 2 pixels on the void, you're not going to be able to magically extract information that's not there. So it's all about setting up an X-ray to get the right resolution of your PCB.
Okay, so if I have like a large board, it would scan the entire image for looking for the gross defects, but then maybe if I have 25 like QFNs or BGAs I want to look at, I would have to have the X-ray walk over to each location and maybe have it like almost like a full screen view for each individual component location.
Yeah, so that is the most likely setup. We can talk with, we have an X-ray partner that we work with actually. If you want to set up a consult, we can look at what resolution is needed. They have automated stages that could get you that higher resolution moving around, and then that could be integrated into the software after that.
Have you worked with Gauge at all? Gauge X-ray?
Gauge X-ray, we have not, no.
It is DAGE.
Oh, Gauge X-ray. No, I don't think we haven't worked with them, but again, there's no reason there's no reason that we couldn't integrate their x-rays into our system. Are you guys currently using Dej?
Yes. So
Yeah, it's normal.
I have another question. It sounds like a lot of it is image analysis. However, if like for my SMT assembly lines, if I got data out of, screen print, pick and place, all the way down the line, it will work with numerical data too, as far as like offsets or, mispicks or stuff like that.
You can put, you can take that data from your different pick and place machines. We've had some customers ask about, can you take in which boards have been reworked, for example. You can put all of that data into the instrumental system. So then for that serial number, later on when something goes wrong, you can go back, you'll have the images. We looked a lot at the images, and then you would have that parametric data. So that could be, like SMT pick and place configuration. It could be functional test data like ICT test, SMT test, any data that's valuable to look back on later, you could put into the system.
We have a related
Does that answer your question,
question. At 3:58 in the chat log, we have a related question.
Let's see, going back, good questions here.
Dan Fazari.
Yep. So how does it respond to images that aren't standardized if it's translated, rotated? Can we treat it as the same thing? So generally, we try to get as consistent images as possible. We do have some correction for alignment. So for example, our software, our AI can do a little bit of post correction for X, Y, and rotation. So a little bit is okay, but we generally try to work with your teams because we want the highest quality data. It essentially just affects the signal to noise. So like the more noise you have from lighting, it'll make it harder to detect very, very small defects. So more consistent data is better. Let's see, we've got, I think that was the last one in the chat.
Yep, that's it for right now. Does
Excellent.
anybody else want to chime in on any experiences that they've had that they're curious whether this AI would be able to be implemented or any other case studies that you've experienced that we could chat about and share? All right, with that, I'm going to stop the recording at this point, Tobias.
Yeah, definitely.